everybody again, and welcome you all to the INAF Observatory of Abruzzo Colloquium. It is really a pleasure this morning to welcome Professor Brent Tully. Let me thank Brent in advance because he's now in Hawaii, and there it's 10 p.m., so it's about time to go to bed. Yet he's here for this seminar, so thanks a lot, Brent, for staying up this late. I don't think there's much need to introduce our guest today, but very briefly, I have to. Brent is presently astronomer emeritus at the IFA at University of Hawaii. He has a long record of publications and prizes for his works, mostly on galaxy distances and velocities, distribution of matter on large-scale structures, and not to mention also the amazing outreach activities he's been working on. So Brent was a pioneer of what now is called near-field cosmology. His studies led to several now very popular discoveries, like what he calls the luminosity line-width relation, which is more commonly known for us as the Tully-Fisher relation used for deriving extragalactic distances. And in recent years, I found that Brent is much interested and a leading scientist in some of the distance indicators, which we in Teramo, the Observatory of Abruzzo, and more in general, the Italian community of astronomers is a lot familiar with, like the tip of the red giant branch. So this morning, Brent's talk will cover some of his latest works and discoveries. And that's more than enough for me. Let me give the microphone to Brent, which will give a talk with title Cosmicflows. Brent, you have 45 minutes. Please go on.
Okay, thanks, Michele. It's really wonderful to be with you people. I'm afraid it's regrettable that my camera is not working so that you don't see me here, but maybe that's just as well. Perhaps it's more interesting to see my slides anyway. So with that, I'll tell you about this Cosmicflows program. There's a lot of people involved, and Michele is involved in the surface brightness fluctuations component that we're linking into Cosmicflows. But for the core program that we've been working on for about 15 years, you can see the people involved here: Hélène Courtois in Lyon, Yehuda Hoffman in Israel, and Danielle Pomerad in Paris. And well, let me just remind you that you've all now seen lots of simulations of a universe, how with the passage of time, gravity pulls matter into the higher density regions and creates these filaments and knots and voids in between. But these, of course, what we're seeing here is a pretend universe. It's not the real universe. And so it would be awfully nice if we could see the real universe in the same way, with the same with a lot of the same ways that we see simulations. Wouldn't that be nice? So here's a little simulation here then. Well, this is the real universe. This is the real universe. The gray there is the Milky Way's projection on the supergalactic coordinates. Individual galaxies are given colors by their redshift. So over here, I guess, over here is the Perseus Pisces filament, and the Virgo cluster is over here. This is in projection on the sky, but we want to see things in 3 dimensions. So let's see what that looks like in 3 dimensions, going out here in this sample out to 8,000 kilometers per second. And you can still see these filamentary structures, like the Perseus Pisces filament, for example. So we're down here at the center. And of course, there's a zone that's obscured from us due to the plane of the Milky Way. But if we go in here and visit our location, so each of these are real galaxies at real positions. And we come in to where we live in the local group. And the bullseye is centered on the Milky Way, and adjacent is our companion, the Andromeda Galaxy. And around us are familiar groups, Centaurus, M83, M81. And most of these nearby galaxies are in a rather narrow plane, which we've come to call the local sheet. And there's a big void up there. We're not very inventive with our names. We call it the local void. And just down the road is the Virgo cluster. 6, 10 to the 14 solar masses, 1,000 galaxies, I suppose, if you get down to the little ones. So that's our neighborhood. Okay, so we've been collecting distances to galaxies, and in the most recent completed edition, the Cosmicflows 3 edition, there were 18,000 galaxies with distances. And here they are projected onto the sky. As you can see, we're going across a scale here of 1.3 billion light years. And the colors here are indicating motions toward and away from us, blue towards us, red away from us. And again, there's the obscuration caused by the Milky Way there. And you can see, in fact, in Cosmicflows 3, there's a lot more objects to the left than to the right. And that's because we had, in Cosmicflows 3, a lot more distances in the southern hemisphere. That's going to be corrected in Cosmicflows 4. But that's the way it is in Cosmicflows 3. Well, you're all familiar, perhaps, with what Redshift surveys have shown us. So the earliest one in the 1980s, the Center for Astrophysics survey taught us about the Great Wall, the Center for Astrophysics Great Wall. And later on, the Sloan people found something that's been called the Sloan Great Wall. And these are on the same scale. You can see here that the Sloan Great Wall, we're going out in the extreme here at about almost to 30,000 kilometers per second. So each of these dots, and is a galaxy located in just from redshifts. No distances here. So that is the way people have worked a lot with redshift surveys. Observe the distribution of galaxies, assume that the mass is distributed like the galaxies, and that allows you to predict the velocity field. Now, there are deficiencies, incomplete sky coverage, this assumption about the mass following the light. And then there's no constraints on what's going on beyond your survey, which can be quite significant in terms of the tidal influences. So we're going to do things a little bit different, the opposite way around. If we can observe peculiar velocities of galaxies, then we can predict the density field. See, we're going backwards on what is normally done. Now, deficiencies here are that the peculiar velocity uncertainties are quite substantial, and they get worse as you go to larger distances. But there's general agreement between the two approaches. And it's then compels us to think that we're on the right track in a basic way, that it's, if we're assuming Einstein or Newtonian gravity and the standard lambda CDM model Now, that might not be exactly correct, but at least it's doing a pretty good job. So in the Cosmicflows program that I'm talking about here, what we want to do is measure galaxy distances. That's our product. And we can get peculiar velocities out of that, because observed velocities, that's easy. If we can make distance measurements, though, we have a Hubble constant that's consistent with those distances, then we can take off the cosmic expansion part of the observed velocities, and what we're left with is this residue, the peculiar velocity. And you know, there's a lot of dispute about what the Hubble constant is, but what we ask for here is a value of the Hubble constant, not necessarily the correct value, but a value that's consistent with our distances, so that on average, we have a Hubble constant that's on average equal to the velocities we observed divided by the distances that we observed. Now, if we've got these peculiar velocities, then in linear theory, we can get the density distribution, because it's just related then to the gradient of the velocity field, where this only what else you have here is the Hubble constant and the growth factor, which depends on your cosmological model, which we assume to be a lambda CDM model. Okay, so we've gone through these iterations, Cosmicflows 2, 3, and we're working on Cosmicflows 4. And we use all these different techniques that I'm showing you here. The two that are identified in red are areas where we directly work ourselves. Our group is working on getting tip of the red giant branch distances from observations with Hubble Space Telescope. And we've been getting these luminosity line with results for the last 20 years. But we're also taking other methodologies out of the literature, these basic things like the 0 point from RL array and eclipsing binaries and things, and then the Cepheid period luminosity relation. And we're also getting these important other methodologies, the surface brightness fluctuations, type 1a supernova, fundamental plane, and we're putting all that in and making sure that they're compatible with each other, so that when two galaxies or a group of galaxies, a cluster, which must be a singular distance, that all the different methodologies are giving the same distances on average to those entities. And in Cosmicflows 3, we had 18,000 distances. And this just shows you a histogram of those of that data, where in orange you see this very dominant component, especially at large distances in the southern hemisphere, coming from the 60F fundamental plane survey, but it's all at declination less than 0. And most of what else is here is the luminosity line relationship. Down in close here, we have this very important tip of the red giant branch information, and we've got supernova going, not that many in Cosmicflows 3, but going across this whole velocity range. Well, here's an example of one of these things, the tip of the red giant branch distances. So here's perhaps this picture here is to show you a red star at the tip of the red giant branch. So let's look at this case on the left here, Holmberg 1. It's at a distance of 4 megaparsecs. And you can see here the red giant branch coming up to the tip here, which is so well defined. There are asymptotic giant branch stars on top. Here's the main sequence coming up here. So there's lots of young stars. There's helium supergiant burning supergiants up here. And if we were to be able to see the sun or a star like the sun, it would be way down here on this plot. So these are only the very brightest stars in this galaxy. But the tip is well defined. We get a very good distance. And here's some other cases here. Here's a case out here at 8 megaparsecs, and here's the tip here. But it has lots of young stars here. And here's a case over here where there are not very many young stars. There's basically a giant branch, red giant branch. And we can measure this to 5% distances. And you can be convinced of that when you come over here, and you can see here these ticks here. So these ticks here are 0.2 magnitudes, which is 10%. So, you know, going from here to here, that's 10% in distance. You can see that by eye that this galaxy, you can easily get it to a few percent. And then there's this luminosity line width relationship, and here's just examples from a recent study. This is line width along here, how fast the galaxy is rotating. This is how bright it appears to be, the bright end up here, the faint end down here. And okay, here's, so this is the relationship. Big galaxies rotate fast, little galaxies rotate slow, and they have this nice relationship here. And then if we look at just cases where there are tip of the red giant branch or Cepheid observations as well, so that we have an absolute value, absolute scale, then this is the current status of observations here. And the slopes that I've imposed here are the same. Just to remind you what's going on here, we can measure, we go to a radio telescope, get a line profile like you're seeing over here, and we can measure how wide that is. That's indicative of how fast the galaxy is rotating. Of course, we have to take into account its inclination, and that's a whole story in itself. Then we get the photometry, and we can do that at various pass bands, all the way from U-band up into the infrared, up to 3 micron, 3.4 microns, or 4.6 microns with WISE. And we get a good relationship in each of these cases. And now most recently too, we've been looking at the baryonic version of this, where now here's line width again, how fast the galaxy is rotating. But now what we're plotting up here is the so-called baryonic mass, where that's the product of the stellar mass and the gas mass. This 1.33, the 33% of the gas is helium, so we correct the observed hydrogen mass by that. And this is the luminosity in a given pass band, and this is then the mass to light ratio, the average mass to light ratio in that pass band. And we've just submitted a paper on that, the Sun, Kortchi, and myself and others, for it's going to give distances for 10,000 galaxies. Well, we saw this this projection of the local sheet early on. Just a reminder then of it. There's all these groups around us. What we have here in red are the major galaxies in the local region. Around them in blue is the virial radius of the halos around those objects. In green is the infall region, now approximated by circles, and they're not circles, but to an approximation, then these green dashes show you the infall regions. And actually then in this, what is this color, teal or whatever that color is, orange, that's to an approximation, that's the region around each of these halos that will ultimately collapse. And anything that's outside of that region is bound to rush away with the expansion of the universe, the accelerating expansion of the universe. And the Virgo cluster is up here, and I'd just like to show that here's the current infall region around zero velocity surface around Virgo cluster. And this is the region that will ultimately, anything in this region will ultimately fall into Virgo. So here's, so the tip of the red giant branch information is extremely valuable because of the extreme accuracy that we have. And also from the fact that nearby, there's not much, the cosmic expansion is not large. And so the peculiar velocities is actually a substantial fraction of the observed velocities. And what we're seeing here then are the peculiar velocities after we take out the cosmic expansion, where we're seeing blue as being peculiar velocities toward us and red are peculiar velocities away from us. And you can see quite clearly some patterns here, namely this whole region underneath here, which is mainly what we call the Leo spur, is rushing toward us. And if you look, here's the Virgo cluster over here, and there's a lot of red over here. So there's, as you get towards the Virgo cluster, there's a rush away from us towards the Virgo cluster, which is Virgo infall. Now, the other thing that's prominent around us here is the local void. And so it's evident enough why the Leo spur seems to be rushing towards us. Namely, it's not. Namely, what's happening is that we are being repulsed from the local void. And so we are moving downward to the right. To the right a bit towards Virgo cluster, down towards the Leo spur. And the Leo spur does not have that much of a peculiar velocity. So it's so the motion that we're seeing there is a reflex of our motion downward away from the local void. And here's just down here on the right is kind of a cartoon of that. And here's a picture showing our motion then towards the Virgo cluster. And we can identify from the gradients in the velocity field, we can get the eigenvalues of the peculiar velocities. And if you have eigenvalues indicating collapse on 3 scales, you're talking about a knot. On 2 axes, you're talking about a filament. On 1 axis is a sheet. And if you have expansion on all axes, you're in a void. And we can do this locally then at all locations in the field. Well, then we can model then the peculiar velocities nearby. And this is, over here, we have the Virgo cluster, the big red dot. The Milky Way and Andromeda galaxy are these 2 black lines here. This is a model we derived from a numerical action model. So it's a nonlinear model, which it has to be to effectively get the motions nearby. And you can see here then motions over the age of the universe modeled in this way. Okay, so we're having lots of fun with this sort of thing. Here's the same thing, numerical action model, but now we're looking just at the local group. So this big white ball over here is the Virgo cluster. And the 2 white orbits here are, on the left here is the Milky Way, and on the right is M31. And in particular, we don't have all the nearby galaxies in here, but we have a whole bunch of the companions to M31 because they tend to lie in a sheet. And this was an analysis trying to understand how come they lie in a sheet. But you can see that M31 and Milky Way are on their way to colliding in about 5 billion years. So we can go to larger scales. And you can see then this little model here of flow patterns. We're here in the center, and we're part of a flow pattern here that you can see you could draw a boundary around this, right? This is what we call Laniakea. And this is over here is the great attractor region. Over here is the Shapley concentration. Coma is here, Perseus Pisces is over here. And you can see that we're starting to break up the universe into these different watersheds, if you like. And here is then something we published 5 years ago or so when we identified Laniakea. And again, the great attractor is in this Hydra Centaurus area. And we're kind of near the edge of Laniakea, towards the Perseus Pisces region. And in here, you've got the local void creating a separation. And there's these other voids around. Over here is the Hercules void separating us from Coma, and down here there's a very large sculptor void. So one thing that we know very well from cosmology is that we're going somewhere at about 600 kilometers per second, and we put down so we observe in the microwave background, we observe this hot spot in one direction and a cold spot in the other, and it's telling us then that we're going somewhere. And here's the vector of it, and here we are, and it's going through pretty close to where we call the great attractor. It's pretty close to what's called the Shapley attractor, Shapley concentration. But we also notice that it's almost exactly opposite a big empty area in the other direction that we've called the dipole repeller. Not that we're not invoking that there's anti-gravity, but there's just not much there, and that has the sense that acts then sort of like a repeller, just there's nothing there. Now, if we take out the main bulk flows though, and look at more local flows, we see then that there are these filaments, and here's the Shapley concentration. Oops, I went a little fast. Oops, just a minute. Yeah, you can see that there's these places then where, well, you saw before. Oh, I guess if I do this. Yeah, so here's you can see there's these flow patterns into the knots along the way, and we can do those separations then. So we can take this velocity field. This is kind of in this picture here, we're at the center, and all these blue vectors are peculiar velocities toward us, and red vectors are peculiar velocities away from us, and we can then reconstruct the density field, and we can reconstruct a map like this. So this is the high density regions around us. And now these are voids then. We put in colors here. The black somewhere in the middle here is the local void there in there. Blue is the Hercules void. The yellow is the sculptor void, and then green are other voids at larger distances. Here we are just showing the voids. So we can have fun showing these sorts of things here. And I guess we're gonna just zoom in here just to look at the local region. And here's the local void. This is Perseus Pisces over here. The Virgo clusters in tight there. These arrows are 5,000 kilometers per second long. And up here we have the Great Wall, and Hercules is up here. And we can just show the local void. Okay, so we do these kind of models. Now, I just really wanted to come down here towards the end, talking about something we've come up with, the South Pole Wall. This is a very large structure that happens to peak at the celestial South Pole, and so it hadn't been very well studied. Well, it hadn't really been studied at all. It's at about 12,000 kilometers per second at that point. And here we can look at it in 3 dimensions. And going all the way from the South Pole region, all the way over to the to Eridanus Chaetus. This is over in the Perseus Pisces region, and here we're just showing a comparison in its dimensions with the Sloan Great Wall, and it's very similar in dimensions to the Sloan Great Wall. Only thing is, the Sloan Great Wall is at about 22,000 kilometers per second, and this is at 12,000 kilometers per second, so it's half as far away, and it's almost this big, and it's a lot bigger than the CFA Great Wall. So there are large structures around. And we can show motions then of, I guess I got to start this. Now, in the 13 billion years of the universe, we don't go very far. We only go 3 or 4 megaparsecs. But if we look at the streamlines of, if you looked at where we would be going and then where we're going after that, you would be able to connect up these flow patterns in the way that I'm showing here. We live in this region here in red, and that's the great attractor at the center of that. Perseus Pisces is over here in blue, and in black, the culmination of the flows is in the Shapley region. So let's see that a little bit more. I'm just running it again. So here's the South Pole Wall down here. Shapley's back here. This is the South Pole Wall running all the way over here until you get to this other watershed, which is Perseus Pisces. And then separated from it and buried in the middle is our Laniakea, where the flow patterns are going to what we call the great attractor in the vicinity of Centaurus, Hydra Centaurus, and Norma clusters. Well, okay. I just want to wind up then by saying that Cosmicflows 4 is coming along. I'm giving some numbers of the kind of what the contributions of each of these things that we're going into it. So we have almost 500 tip of the red giant branch distances coming from Hubble Space Telescope observations. From the literature, there's now 57 Cepheid period luminosity distances, and there are 6 maser distances. Now, the maser distances it's rather interesting. NGC 4258 is the main case there that people are familiar with. So it's a real anchor then to the cosmic distance scale. There's 5 more larger distances with relatively large errors, but with an independent 0 point. I mean, the 0 point is not coupled as these other, the tip of the red giant branch and the Cepheids are coupled to our measurements of within our galaxy. And hopefully that Gaia, for example, is going to affirm what the 0 point is for the tip of the red giant branch and Cepheids. But these then are the cornerstones of the whole operation. Now, Michele has been involved very much with surface brightness fluctuations. Well, we have over 400 right now. A lot comes from him. We have a program, in fact, with Hubble Space Telescope to make more of these measurements. So there's more that are not, they're coming along. Surface brightness fluctuations is an important methodology because you can get distances at the level of 5%, and we can get hundreds of them. And they're at rather large distances, out to 100 megaparsecs or so. And so that's going to be increasingly an important part of the distance scale operation. Now there's supernova. Obviously, this is something that people are more familiar with. We have almost 1,000. I'm hoping, in fact, we'll get a few more here. We might actually get up to 1,000 in Cosmicflows 4. This would be by far the biggest collection of supernova. These are 815 supernova within a tenth the velocity of light. All of these distances are within a tenth the velocity of light, 30,000 kilometers per second. Well, we have 100 supernova type 2. It turns out that they're not as accurate. So supernova type 1 are good to about 7%, whereas supernova type 2 are only good to about 15%. But okay, we can use those as well. And then there's these other two, the fundamental plane, luminosity, line width. And that's where the numbers are very large. The errors are also large. Fundamental plane uncertainty is about 25%, 25 to 30% per object. In Cosmicflows 3, we had about 10,000 fundamental plane in the southern hemisphere from the 60F. The big jump here is coming from using Sloan photometry and velocity and spectroscopy. And we have about 30,000 fundamental plane observations in the north, celestial north galactic quarter of the sky. So we're going to have very good coverage in that sector. And then we've got these luminosity line with distances that are good to 20-25%. All told, something like 50,000 galaxies. And we've got all of these things in hand, and right now all we have to do is link them all together, and in a great MCMC Bayesian linkage through the commonality of observations of individual galaxies and in clusters. For example, in Cosmicflows 3, in the Virgo cluster, we had something like 170 distance measurements. So we're going to have even more than that now. In the Coma cluster, there's over 100 distance measurements from different methodologies. So it gives great linkage between these things. Supernova going off in the Coma cluster, and then the surface brightness fluctuations, fundamental plane, and luminosity line width. We have, in that cluster, we've got 10, 15, 20 observations of each of these things. Well, not that many supernova, but a few supernova. And so that's going to give the linkages between them. Well, I think that's what I wanted to talk to you about. So I will give you this pretty picture, and I'll sign off from this talk. Thank you. Thank you for hearing me out.
Thank you, Brent. Thank you for staying out this late.